over to you.
Thanks very much, Mohammed. Before we start, I'd like to acknowledge the Gadigal people of the Eora Nation, on whose ancestral lands our city campus now stands. I'd also like to pay respect to the elders, both past and present, acknowledging them as the traditional custodians of knowledge for this land. I would further like to acknowledge the traditional custodians of the various ancestral lands from which our other attendees, including Sascha, join us today, and to pay respects to those elders past and present. And I'd like to make a special welcome to any Indigenous people in the audience. So it gives me great pleasure to be able to introduce Sascha, a great friend, and I know a very close friend of Tim's as well, a collaborator, and just someone who is very impressive all around. So it's fantastic to be able to bring him to UTS and to show the work. Sascha is the Australian Director of Bollinger+Grohmann, which is an incredible achievement in itself. Bollinger+Grohmann, for those who don't know, are the engineers responsible for an amazing suite of projects across the globe. Sana's Rolex Learning Centre, for example, all the best Carl Pimmelblau projects, for those in perhaps my generation more than the current. Still cracking out great projects with the support of Bollinger+Grohmann. Importantly for the students in the audience, Bollinger+Grohmann with Clemens Preisinger are the developers of Karamba. Everyone in the 3 subjects that are the kind of this lecture series is supporting are using Karamba, and so excited to, I'm sure be very excited to see some examples of that in practice. And the title of the lecture is Parametric Engineering, incredibly important as we're starting to more and more embed computational tools into the practices of architects and other forms of designers. It becomes even more significant and valuable that our engineering partners, and when we're lucky enough to work with people like yourself, Sascha, that you can extend the same extend support and even bring greater ambition to the sets of methods, much more powerful when they're on both sides of the design and engineering table. So without further ado, thanks very much. Welcome, Sascha. It's great to have you, and take it away.
Great. Thank you, David. Thank you, Tim and Mohammed, for the kind introduction, and also for the invitation to this great lecture series. I've followed a couple of those online as well. It was really nice to see. And a very interesting topic in general, obviously, always keen to see what others are doing in that realm. So for the presentation today, that I'm sharing in a minute, it's basically a quick introduction of the global practice. As they've already said, some of those projects I'm pretty sure you know. Some others, more in the local context, are maybe not as known, but nevertheless as complex, or maybe sometimes even more complex than the big major player projects or milestone projects. And so this presentation focused solely on local Australian projects, because I thought it's nice to see that what is possible in Australia, but always with obviously the bigger picture of collaboration, material properties that we usually tend to forget mostly once we try to work on a project, and that leads then to a range of different assumptions, and then also form optimization as one of the main drivers for our work that we are trying to achieve with the architects together. Okay, sharing the slideshow now. Okay, so parametric engineering from material performance to form optimization. A little bit of background of the practice. Bollinger+Grohmann is an international operating engineering practice, but they have also their own architectural branch in every office, basically. And those architects, they are specialists, geometric specialists, computational specialists, and they're usually supporting them in-house, but also obviously the architects that we collaborate with to achieve their goals. So as you can see, mainly it's a European-based office. We have two almost satellite offices, if you want to say. One is in China, the other is in Melbourne. We had one previously in the States and in South America, but this is now our core business, and yeah, growing. So the services that we usually do and perform are structural engineering, facade engineering, and building physics and simulations. One of our bread and butter areas is fire protection and site supervision, but then we also do a lot of work in geometry and BIM and detailed design areas. And all these areas usually get support from our computational design team as well, in one way or the other, because we feel this is a very important, not only tool, but also philosophy to be integrated in the daily work and life of everyone in our office. Some of those milestone projects that I've already mentioned, what you see here, a lot of co-Pimmelbrau projects. We are the main lead engineer for all of them. And some of the examples you can see here is the BMW world. And one big project in China on the bottom right, and the European Central Bank almost in the bottom center. Then we have a lot of work with Sanaa. You can see the Railroaders Learning Center. You see that really wonky tower here that tries to deform a little bit, which is they called it the tower with a hip. That's the tower by Bjarke Ingels Group in Frankfurt. We are responsible for the hip. Everything else is pretty straight on the tower. And then on the left-hand side, is one of the largest towers in Austria that's designed by Dominic Perrault. Those are some of the milestone projects, but obviously every engineering office has to focus not only on the big ones with the big names, but also on small scale projects, not only out of the necessity to earn money, but also to use those small scale projects for in-house R&D mostly, and also to have a bit of fun. So we work on every size, topology, complexity, and with every material that we can find and get our hands on. And why are materials so important to us? I like to show usually this graph, the evolution of materials, which is pretty much outdated already because it was from 1909. And the outlook, obviously 2020 is past us already. And the development in the last 10 years from 2010 to 2020 was definitely more potential as the authors envisioned. But the good thing about this graph and why it's so interesting is to have a look at the curves, where and how materials played a big role in society, in the development of society, and what kind of materials we have to deal with in the future as well, or what we can deal with in the future. So there's definitely a shift from the 60s, where everything was metal focused, towards 2020 nowadays, where for now we have a good mix of materials, but polymers, composites, ceramics, engineered timber is something that we classify as a composite material as well. That will just grow and grow and grow, and therefore our available list of materials that we can deal with and work with in architecture and the built environment is just increasing, and we have to be aware of that and the possibilities that come with them. So conventional materials are some of the ones that you see here on the left-hand side, that most of them you can find at any construction site. Then on the right-hand side, you see non-conventional materials that we classified as low-tech materials, which are materials that you usually find in vernacular architecture, but find their way now also back into larger commercial projects, which is great to see. And this is where we feel like is one area of future of materials in the building industry, just simply because of the aspects of sustainable design, the the impact of our carbon footprints. And that's where we want to focus a little more in our in-house research, but also most of our directors and managers have a lecturer position in-house. So they redirect some of their ambitions and their work in the academia. Now we also have non-conventional materials, obviously, that we can classify as high-tech, which is 3D printing, foils, polymers, engineered timber as a classification for non-conventional high-tech, probably almost outdated already. We want to see it obviously implemented more and more, especially in the Australian context, where we have a good market for it as well. And we try to obviously not only push those materials, but the core of our philosophy is we just use the material, the appropriate material for an appropriate course. How do we do this in our workflows? Usually we try to explore a lot of different options and possibilities at very early stages with all stakeholders together, especially with the architects at the beginning, to see what material might have what effect on the design. And one idea is to work with material distribution. As you can see here, this is a little script setup that just works with a similar strategy towards BISO. I don't know if you're familiar about it, but BISO stands for Bidirectional Evolutionary Structural Optimization, which could fill a whole lecture in itself just to talk about it. But basically, the design here itself changes accordingly to the force flow of the volume that is represented here as a triangulated mesh for now. And then it starts to increase mass of a certain material where we need to strengthen it. So everything that is red becomes a thicker wall, for instance, made out of, in that case, concrete. So wherever we need it, we can increase the material, and wherever we don't need it, we can take it away or minimize it, and then it could be a hybrid system out of concrete, steel, timber, steel, or all of it. So with the idea of material distribution, we try to inform a lot of our projects from the small to the large. That's just possible because we have the computational tools at hand, especially, as they've already said, Caramba, which is an exceptional good tool for early stage design work. And the following projects deal with that in certain different levels, in certain different ways. So the first project that I wanted to show you is the Future is Here, which is already fairly old. It's from 2014. That is designed by Studio Roland Snooks down in Melbourne for the RMIT Gallery, and it was for an exhibition, The Future is Here. And the future is here, back in the days, was basically talking about future of fabrication and the idea of fabrication. And for that, the idea was formed that the whole interior design should reflect, obviously, the theme of the exhibition. So also with newly acquired robots at RMIT, we set out then the task to design those tables and awnings and shelves with the robot at hand, and with material that we could increase its stiffness by inserting certain elements, just to create the illusion of something floating very thin, and is still able to support the exhibition pieces on the table itself. So here you can see a breakup of the different components. We decided to go with a fiberglass composite, and the strengthening of the system would occur with foam inserts which were milled, CNC milled, and then we would have additional extruded inserts, which would be extruded by the robot. And this is basically creating a sandwich panel. You can see it here. The whole build up, if we go into the thinnest area, is just 5 mil. So the table deck is 5 mil and can span quite a long span. And this is only possible by working with the idea of material distribution. So wherever we need to increase the strength, we would redirect those foam inserts and change the cross-section of those foam inserts to create a stable desk. To do this, obviously with glass fiber, it's always a tricky thing, and with a lot of new materials, you have to do first a lot of small tests to really understand the right mix of it, the right amount of fibers, the directionality of the fibers, the right bonding material. So this was done in the RMIT Structural Testing Lab. And all those different tests, there are small samples, created then basically out of those different samples a cross-section that we could assume that the material behavior that we simulate would be close to the reality. And this is something that a lot of people tend to forget if we introduce new materials as well. And that's also why new materials take a long time to find its way back into architecture and the construction industry, that usually you need to have a lot of tests done before you have a library available that you can actually use the material, because all of it is just prediction. And the prediction is based on data that you collect, and there's no 100% security that it will actually behave as you try to predict, which is something no client wants to hear, but that's the truth. And so the more tests you do, obviously, the more you come to the truth of the behavior. But for small-scale prototypical projects, obviously, there's usually enough if you do 5 to 10 samples of a certain test and conclude then the outcome. And you can see the test results of that little cross-section that we were building compared to a regular material that is available on the market, compared to concrete, steel, or just the pure fibers itself. We were at around, it's a bit small now to see, but we were at about 250 MPa, which is a little bit lower than steel, but much more than concrete, which was good enough for us to go ahead with the material. So, and to start off with the material distribution, we designed, obviously, first a pattern that we wanted to work with, and then the pattern and the geometry of the cross-section would vary depending on the stress distribution. To do this, usually we have an evolutionary algorithm in the background, and we need to feed that algorithm with a certain information. Here it was that we give it one certain cross-section, and the whole geometry was populated with a cross-section. We set up then all our parameters. We set up where we want to fix the model, the geometry, where we want to apply certain loads to it. And then we give it a first set of cross-sections. And those cross-sections are designed so that they can change according to certain parameters. So they can change in width and in depth, and obviously the angle as well. And then it starts to apply this first set after the first iteration with a regular cross-section. And then it runs through an iterational process to determine and reduce stresses in the overall system. And wherever we have dark red, doesn't mean it's breaking. It just means that there's the highest area of compression, and where it's blue, it's our tension area. So, and we wanted to have a system that has a very even distribution, because in that way we are quite sure that the system is behaving in a normal way. So for installations, obviously it's not as stressical, but no one wants to go close by to a shelf and see the shelf bending, because then they get scared and they leave the exhibition. So there's still some minimum requirements there for structures like that to deflect in a certain range. And once that was fixed, obviously it went into the fabrication mode, which is then a bit of a break if it comes down to those advanced materials, especially the composite materials, because there are no real automated processes in place. All of it is manually driven. You can produce the formwork, you can create the formwork, you can do things to make life easier for the people who will make it, but in the end of the day, it's just a very labor-intensive work. And only good skilled people should do it. So most of them, there are boat builders. Here you can see just a little detail that even the fixings were embedded in the carbon fiber and glass fiber composite to hide any fixings. And there you can see some of the first large elements with the distributed foam pattern inside. And here you can see the final results, the tables and the awnings. And the edges, towards the edges, it was really just a little bit less than 5 mil thick, very translucent glass fiber composite, which was nice to see. This was one of our first experiments with glass fiber in itself and with the idea of that material distribution in a smaller scale setup. And out of that, we're going bigger and bigger in the next projects. So this is the next project that deals with a similar idea, but then still slightly different. So this is the Saigon Welcome Arch, designed by McBride Charles Ryan, and it's in Melbourne. Tim, I guess you know it quite well from your previous days in Melbourne. And this project is a welcome gate for the area of Little Saigon in Footscray. So it's for the people. And the idea there was really to reflect on the tradition and the culture. And those two birds are resembling cranes. And those cranes create this arch. They can just pass by or have rest underneath them and just enjoy the scenery. So the problem that we faced with this sculpture was, first of all, obviously the geometry. It's very bespoke, and it's also very thin compared to other structures of that scale. So it's a very fragile system. And also we had a very worried client at the end. He wanted to make sure that this will stand up, even if the car is crashing into. So we were designing this system in two ways, parallel. So one was the design that the architects wanted to have, and one was that the client wanted to have. And we had to make both of them happy. So how did we do this? Again, we utilized Karamba as our main driver for the initial design processes. And here we, after a lot of geometry manipulation back and forth between the architects and ourselves to optimize the structure, to find a suitable structural system in it, we started to generate the client's version, which is he wanted to have an internal steel frame and everything would be clad with glass fiber composite panels, which was, in his view, the safer option and the cheaper option. So we started that process by creating these center lines within the volume of those sculptures. And because there's not a lot of room to move around within the void of those cranes, because they're, like I said, very thin, we developed a range of different scripts that try to align the lines in the center between the void and also tried to rebuild the curves so that we can adjust them towards the curvature as required and necessary. And then we started to apply actual cross sections around those center lines. And then we had to rotate those cross sections a lot of times to find then the actual deviation between the outer surface, which would resemble then the glass fiber plastic outer line and the inner line, so that we don't create any clashes and still have enough space to mount the panels on top of the steel. So there was a lot of cross-checking and tolerance checking, class checking involved in the script before we could actually start to analyze if what we're building there is actually possible. From there, we then started again with our Karamba implementation and started to iterate through points 4 to 7. So every time we applied cross sections, tried to analyze it, and then we went back to the origin as we found that the structural system was not efficient enough, and then we had again to rebuild the cross sections, find the clashes, orientations, until we had a new version of it, and then we could analyze it again. Thankfully, with computational design, this is a very quick exercise and not something that takes hours or days, as you would imagine if someone would model it. And then the outcome was then something that we could very quickly reiterate. And you can see here that obviously we still have a lot of different cross sections, but most of them are very gentle in its changes, which meant that you could almost build the entire sculpture out of 5 different cross-section types. But again, because it is a curvy, very elaborate geometry, every steel builder and welder, they already were scared of the job to really cut it all accurately together and design it towards our goal. So again, it's a sculpture. You don't want that people are too afraid of walking underneath. So the basic criteria to finalize the geometry is twofold. One is the deformation that it will occur. There's no structure in the world that is not moving, but you just want to limit that. And the other part is obviously then the buildability of the system based on the material and the structural logic behind that system. And then the second part was obviously the idea that we developed with the architects together, which was our preference, that we built the whole entire crane without any internal steel structure, and it's just glass fiber reinforced plastic elements that get bolted together. And there again, it was a lot of geometry optimization necessary, because for those panels, the glass fiber reinforced plastic panels to be built, obviously you have to break them down in certain segments, and this had to be reflected in the overall geometry. Then we went through a series of iterational analysis processes, which were then outside of Karamba. It was another very bespoke package that we're using. And there we could iterate through wall thicknesses very quickly. So every state reflects a different wall thickness, and therefore we could see different results very quickly. And you can see that obviously the maximum deflection versus the wall thicknesses, the thicker the wall, the lower the maximum deflection. But at the end of the day, we couldn't really go any further, because otherwise then it's a too thick glass fiber reinforced plastic wall to be built. You have a lot of tolerance issues the bigger and wider you go. So we couldn't really aim for the target that we wanted to set ourselves for the deflection. But then we just started to combine glass fiber and carbon fiber in the system. So locally strengthening the cranes where we need to with a similar material system, but a different fiber. And that reduced the deflection exactly to the point where we wanted it to have. And you can see the outcome. And that's the great thing, something that you most likely never were able to achieve with precast concrete elements or just with steel and then the cladding option around it. It's a very seamless geometry, very true to its original geometry that you can only build with those glass fiber plastic elements. From there, from this project onwards, with the material distribution, we again make one step into the larger projects, which is the Monash Business School in Melbourne, designed by NH Architecture, and for the Monash University. And they had the brief of that existing building that you can see on the right-hand side to design, they claimed to be a pavilion, a very lightweight pavilion for the Monash Business School for the students, with, as you can see on the left-hand side, meeting spaces, library, connect to the campus, bit of wind protection and sun shading. So nothing really big and elaborate, but once architects, I guess, go and start, they find ways to increase the program. They try to increase the building volume, which is great, because otherwise you get stuck with the same old. So you want to have the challenge on both ends, from the architects, from the clients, and also from the engineers, to design something worthy. So this was the initial design that they came up with. It's slightly bigger than they pitched at the beginning. So it's a bigger conference room with a big staircase, and the staircase is then going into the existing building, and you have some other spaces there as well, some meeting areas. So initially, again, everyone was quite worried about the complexity of the project, of the geometry. Therefore, the go-to strategy to value engineer everything is make it as simple as possible. So the proposal was first, obviously, to build everything out of regular framing, which every builder loves. But at the end of the day, we added up the whole weight of the framing that we had to use just for the pavilion, but also because we couldn't touch the existing structure. We needed to have a very heavy transfer structure, which in that case was almost twice as heavy as the whole pavilion itself. That increased the load capacity of the columns of the existing building. You can see them here in yellow. Everything that is in yellow is basically not working. I tend to use yellow instead of red because it looks calmer. So people don't get too scared immediately. So the problem was, obviously, it's too heavy for the building, which you can usually compensate by re-strengthening the building. But on top of that, there was also some acoustic issues with those stud walls, so that they were not actually meant to create a nice acoustical environment for conference rooms, for instance. There would be a lot of additional work required to come to a fairly good standard that the university wants to have. So after all that research and all that initial work, everyone thought, okay, we can't really do it. So we have to go back to do something else. And then with the discussion with the architects and ourselves, obviously we wanted to have this project in that specific form. We tried to find new ways of building it. And in that case, we went to CLT, because CLT, cross-laminated timber, is a material system that is very strong and very robust. It's very quick to fabricate and build as well, to install. And because it's timber, obviously it is lighter than steel. So with that option, we could not only reduce the weight by a fair margin, so the transfer structure, the weight was almost reduced by half, just because we had a lightweight, or lighter, not lightweight, a lighter pavilion on top of it. And also because of the CLT itself, it has a certain mass that the acoustic engineer could also utilize to work for the acoustics as well. And you can see some of those interior images of the final outcome. So this is the conference setup on the left-hand side. The whole staircase has then the CLT exposed, and this is how it looks, the golden jewel from the outside. And then from this project, I guess we go a little bit smaller again. It's an intermediate size, I guess, between the projects that you've seen so far. And this is the Interchange Pavilion. So all the locals in Sydney, if you haven't seen it yet, you have to go there. I can't go there because I'm stuck here in Melbourne, but you should definitely go and visit it. It is a remarkable pavilion designed by Studio Chris Fox. And the idea was to have, obviously, a new place that anchors the new development there in that area. And the idea was to have these leaf-like structures, and they sort of create a nice protected area that people can just mingle, and also use it as a performance stage at the end. For us, again, it was very mundane, I guess, our first approach. We wanted to have it also very simple setup. You can build very quickly, and everything else, the whole form and shape, would come out of the cladding system that was proposed back in the day. When we started the work, the cladding system was not quite fixed. The ideas were precast concrete panels, timber, even steel cladding. Everything was on the table. And for us, it was then an iterational process again to find the best form and the best material distribution, as we've done in the past as well. So there was a lot of iterations over iterations of finding the correct outer form of the pavilion, because those leaves had the tendency to fall down because they don't really have the curvature required that we needed to stabilize a little bit. So this was one process. The second process was definitely to look into the internal structure and the distribution of the forces, and hence you see there a lot of different cross sections that were then able to build the pavilion. And this was then also an iterational process that we've done on our end, obviously with computational tools. So we checked always the overall weight and the displacement of the pavilion substructure or the steel framing to come to a conclusion where we feel confident that the displacement is within the range. The overall weight of the pavilion is sort of in the range, because obviously if it's just going up and up the weight, then you have to redistribute all your money into the ground and no one can see it because it's just foundation work, and everything on top will be then scrutinized because there's no money left. So you want to have a good offset of it in terms of having a good fit for your groundwork versus where the money is, the actual geometry. But with all this in mind, we couldn't really find a suitable way of the overall weight with this displacement distribution, not only because of the weight, but also it was very complex to build. It's not only a grid that we established, but it's also all sorts of different angles and areas that had to overlap and be connected. So a lot of bolts, a lot of welding, a lot of little elements, and that simply blew up the budget. And from there, we had to go back and find again another strategy of how to build it. One way where we thought we could save a lot was then just to exchange the steel frame with an aluminum frame. And we started to work with the similar grid, similar displacements that we wanted to have, but then try to see if we can reduce the weight. And the weight here could be drastically reduced at the end. So previously we had somewhat about 15,000 kilograms, and here we have 9,000 kilograms, and displacement is in a similar range. But it was still very complex to build. So then we went over another series of investigations of how to build most appropriately with aluminum. Because this is a very large structure, no one in the building industry has a real clue of how to build with aluminum. There are no real codes and guidelines for it. There are, again, some guidelines that, you know, very, very small things will be covered, like awnings, facade claddings, but not like a real structural system. So we had lots of discussions with experts in the field, which are, again, boat builders. They're just great to work with. They're better than most of the builders around. They know complex geometry. They know all the materials. And we came up with a system which is an aluminum waffle structure, where all the connections are just perpendicular to each other. And it's just easy, clean welds, no bolting, nothing there required. The only offset here was that all the cross sections are bespoke. So you can't really buy it from the shelf. And the cross sections have to be built by the boat's builder as well, by the fabricator. And it's all out of flat panels, obviously, water jet cut, and then they put together those cross sections. But this was not as a difficult task as we imagined, because once you develop your substructure, and obviously you can then start to create CAD files out of your geometry with computational tools. You can subdivide the system where you need to, and then you can start to basically build every of those ribs on the floor, flat, without any scaffolding involved. Complex setups were basically neglected, and therefore we could go back into a very fairly good range of how to build it, and also the time that this was possible to be built. And this is then how it went from the shop, which was or is still in Brisbane, where you find the best boat builders, and then from that area they were shipped over to Sydney and then assembled and erected and assembled. And there you can see all those little fingers, or the C-shape extrusions. They're there for the cladding, and the cladding is twofold. So the outside cladding is again glass fiber reinforced plastic. Glass fiber reinforced concrete in that case. And then on the inside, it is timber. And this is then the final outcome of the pavilion, which is always fascinating to look at, I find. Yeah, this is my short summary of working with materials and form optimization. Some examples from practice, mostly focusing on the work that we've done and do in Australia. I think I'm a little bit under the time, but maybe that leaves us with more Q&A, hopefully. Nice discussion there. And yeah, thank you.
Thanks very much, Sascha. Amazing work. and really nice way of talking through the evolution and how I really like the idea that you described the small projects as in-house R&D, and it's clear the way you're taking knowledge from one project to the next. So really fantastic. I'll kick the questions off with one of my own, and then we'll hit the chat and the Q&A and see. I think we've got no open questions in the Q&A, so those in the audience, feel free to please type in your questions. My question is, obviously a couple of the people you've been working with, Roland Snooks, or at Chris Fox, I think you had Gabe Arco and other people in the team, some of the employees, where the geometry rationalization component is clearly there, and that set of skills is diffusing. Computational design, I guess, is diffusing slowly through the profession, but those people are among the leaders, no doubt. How is that changing the way you interface with architects as their literacy in computational tools grows? Perhaps in Roland's example, it means the ambition goes up and he just brings you harder problems. Yep. Talk us through that. Obviously, some of the projects you showed with practices where perhaps the project is not so ambitious, but probably all of them have a decent amount of computational literacy in-house.
Yeah, no, most certainly. And actually, it makes it somehow easier for us because then we can tap into that work frame as well. We can, and that's what we like, we can establish more or less the leveling field, all of them at the same level, and understand not only the language, but also the challenges that are coming from complex geometries. And then the workflows, ideally, not always, but ideally then also easier, because then we can build basically a front-end tool for them. They develop their tool or their geometry with our front-end input at some point, and then they can give us their further developed geometry or project in general, and then we can work with that and give them the end piece where we finalize then the solution with obviously structural input or material input or whatever is required. So it becomes an iterational workflow across practices. It's not only in-house anymore, but it stretches over not only maybe one or two parties involved. Ideally, it will be even more. So the builders, for instance, and the fabricators with their knowledge, if they are confident with CNC milling or using robots, their expertise could tap in there as well and be part of that workflow, which is then very exciting to have. But yeah, obviously it's early days still, it takes time. And those smaller projects are definitely the projects where we can establish that already and experiment with it. And hopefully, and then we can take bits and pieces where we see them, more applicable to larger projects. And therefore, then those will become the norm, but there will always be these very experimental phases as well, where we just try new things with everyone on board.
Fantastic. I can see Tim with his hand up.
Yes, Sascha, and there's also questions I want to take. I have got two questions for you, Sascha. Actually, following on from Dave's question around structural form optimization, if you could maybe speak a little bit about good structural form, because there were certainly some projects who maybe had a bit more or better structural form than others, which of course then also gave you certain opportunities to actually explore materials. And the other one, Sascha, and you can choose either to address them both or not, is you start your lecture with a history of the development of materials. And certainly there has been a drastic expansion of our material palette also to more biomaterials. And how you see that currently happening, in the work that you're involved in. And just to talk a bit about, I guess, that part of it, because I know you're very passionate about this.
Yeah, I save that answer for the second question later. The first one with the structural form, most of the geometries that we receive or that we start the conversation with the architects or with the designers have some problems, obviously, because it's not at the forefront of the design process to develop something that has a very clean structural geometry in place. But you can fine tune and tweak it most of the time. So for instance, with the pavilion by Chris Fox at the end, the last project, those leaves, they were at the beginning very slender, very steep, had subtle curves. And if you would take one leaf off, it would just collapse and fall over. So there then the discussion is obviously what can we do to still create the inherent logic and to be true to the original idea by manipulating certain areas to keep it stable. And obviously the easiest way is really to create kinks, similar to the first project, the project that we did with Roland Snooks with a table. If you just simplify it, it's a flat piece of paper and it has creases or kinks in it. And whenever you do this, obviously you create an inherent stability. And that's something you can do for a lot of projects in various ways, either through this thickening strategy or manipulating of the leaf with Chris Fox, that you start to bend it in certain ways. And these are subtle moves, but they do a lot of work for the project, structurally speaking. Ideally, everything is an arch, because then it's just compression based. You don't have to deal with tension, and gravity finds its way. But then, you never would be able to do something like a Cope-Himmelblau building, which has 100-meter cantilever. Gravity is, shouldn't be your enemy, but sometimes it will just throw you a rock in front of you. For the material side of things, the projects that I've just shown today, there are projects still dealing with material palette. That is very common, and there is obviously a reason for it. Otherwise, you have to go through a very lengthy process to get, let's say, biomaterial into the mix, because then you have to do more tests. You have to go through the typical accreditation processes of all sorts of bodies and people involved that want to understand, obviously, those mechanics, the physical properties and mechanical properties of the material, to be sure that is something that we can work with. But we at our end right now, we're working, for instance, on projects that are dealing with 3D printed timber, with earth and mulch bricks. And we have a project right now that we're looking into steel welding printing, so WAM technology. All this is very exciting, and it's very great to see. And it's a combination of the material and the material process and how you can fabricate and build with the material. And I'll definitely see that there's a lot more materials with a more sustainable aspect to it coming into the mix sooner than later. And then it's just also on us to find ways of building with those materials and finding the right tools to work with the material, not only to shape it, but also to design with it. And there's one good example, all the projects at ICD in Stuttgart with Jan Knippes and Achim Menges and all of them, all the carbon fiber woven projects there, they're great to look at, but obviously sustainable aspect is horrible if you look at those projects. But the core idea of it is obviously still you design something new out of the box, you experiment with it. And through all of those different projects, for instance, the engineers found that every time you still have to do your material tests, you still have to do all of those little detailed assumptions that you can't just take from one project to the next, because every project, even though they deal with the same material composition, it's always based on how you make it, how you interweave the carbon, how the carbon is bond in between the bonding agent, and how the robot is taking it around geometry. There are always slightly ever so misalignments that just is the way of the process, you can't predict. So every time there's some way where you have to simulate it, not only on the computer, but also with physical tests to support that. And that's the great thing. I feel like there's still something involved that we can't really 100% rely on the computer only. There's always a portion of material experimentation upfront as well.
Fantastic. So taking some questions, some of them overlap with what we've asked, but we'll ask them again to be true to the people who've typed them, and I'm sure you'll be able to craft the answer in a new direction. So Andrew B says, hi Sascha, great pavilion structure and use of taking complex form all the way to the flatbed fabrication level of drawing. How do you feel the role of the structural engineer is changing as these digital tools are now more prominent in our industry? So similar to my question, but perhaps more focused on the engineer end.
I feel it's definitely enhancing the capabilities of the engineer and also widens the view of the engineer involved in those projects, because then I feel they learn a little bit more of the initial concepts of the geometry and the design that the designer wants to express and work with through the unraveling of geometry. And then there's most likely a tendency to more appreciation of the work on one end. And on the other hand, it gives them also obviously some tools to communicate structural engineering issues with the architect on a visual level, which is much better to discuss also on the same platform, other than just looking at some numbers. So I think with these tools, it's definitely helping from a structural engineering point of view, but from every engineering point of view. So from mechanical engineers, if they have a problem, if they can visualize it computationally, it's much stronger message they can bring to the table, similar to a sustainable engineer. And it's just a way of how we represent data, which is just, I guess, the way that we could use to really identify issues and communicate better between different disciplines, because every discipline speaks a slightly different language, but the visual representation is the one that is always the unifier.
Fantastic. Yeah, I know doing work on the Nest project with Bollinger+Grohmann, then the thing that was most useful for me was seeing just the deflection animations. So watch the kind of the strange kind of dance, the teapot tipping over, was by far the most understandable way to see what was going on. Fantastic. So the next question is from Patrick Dorello. Hey to Patrick, he's a friend of the school for a long time. Patrick says, lovely work and presentation, thanks. Just there is terms of high-tech materials with the shift towards trying to use low-tech materials in response to the climate emergency. How do these digital tools, workflows change with this categories of material? This is hi from Manchester.
Yeah, I think that's obviously similar to what I already referred to with Tim's question, that the tool itself is most likely not changing, which is good, because it's always the same platform that we can use if it comes down to experimentation with the system and with materials. The thing that obviously changes in the understanding of the material and the material behavior itself. So the mechanical values of a material, and also the physical values. And as long as we can use this to inform then our computational tools, then we have always obviously this embedded in our system. And yeah, definitely low-tech materials should be considered most of the time wherever possible, but sometimes still nowadays at least there are obviously issues, mostly with authorities. You know, I would sign off almost every low-tech material that comes across because I believe in them, but every insurer they would say, can't you just build it out of concrete? That's it. But yeah, so there will be obviously not only the conversation and the drive from us as the design team and the engineering team to promote the value of low-tech materials. We have to go the extra mile to convince more people, and once they are on board as well, then everything becomes more easier. So, for instance, if governments try to support it, the rise of CLT is only possible because it not only gets support from the local industry, but from governments and statutes and standards and guidelines that develop specifically for that reason, that people don't fear too much.
Yeah, that's super interesting. A question that springs to mind off that is, how have you found it working in the Australian regulatory context? I know working in Switzerland, we were extremely excited because, I'm paraphrasing, but basically we were told if the engineer says it's okay, it's okay. And they're willing to let the engineer take 100% responsibility outside of the code. In Australia, we have a performance-based code, so in theory it would be true, but it's not quite as permissive.
It's not quite there, and again, for a good reason. No one in Australia, if it comes at least to building, wants to take much of a risk. Everyone wants to be safe, and also the standards and codes, they are extremely on the safe side. So if you go around the world, there are other countries with more wiggle room to explore structures and structural systems. But it's also that therefore some of those materials are not really covered. So therefore it gives you an opportunity, for instance, if we work with aluminum, to say we want to work with aluminum, but then everyone says, but we don't have it in Australia as a standard. And we say, oh, then just take a standard from somewhere else, because it's a material, they can use it everywhere around the world, they know how to do it, we just reference this. And then it becomes something like a performance solution, because it's still based on the code somewhere else, and they can't say anything against it because they can't really verify it from their end. So there's a bit of a workaround there as well, but definitely in Australia it's a bit more strict on the safe side from the standard points of view, but also from the culture itself. I mean, there are great projects that really push the boundaries in all sorts of directions, not only pavilions and small scale structures, also large scale structures in Sydney and Melbourne particularly. But it's always a big push, and it has to be a big push by everyone involved. And it could be a little bit easier compared to other countries, but that's the thing that we have to deal with.
Looking just in the Q&A, there's another one here from Shubhashini. Simple question: were heat gain factors for materials taken into consideration, especially with the pavilion?
Yes, definitely. We have to, because even though it's clad, there will be a lot of heat gain inside the pavilion from Chris Fox. That's the aluminum. Thermal expansions is part of the analysis that you have to do, the detailed analysis at the end of the day, and therefore also allow for certain movements. So if everything is just rigidly together and has no way of expanding slightly ever so, then at some point, if it's too rigid, then it will just crack and explode under its own stresses, whether they are induced by temperature or other loads. So thermal loads are actually very crucial. A lot of people tend to forget about it, because if we feel cold, we just put on a jumper. If we sweat, we exchange the jumper for a t-shirt. A structure can't really do that. It has to be with all the different temperature differences, and then it still has to feel comfortable. So, yeah.
Fantastic. Anthony Nastasi, I think your question's been answered, so I'll skip that. But Anthony, if you want to rephrase it or add a different one, feel free, please. There's a question here that looks to me like it's written by you, Sascha, but I must be reading that incorrectly. Are you feeding questions to yourself? Unless that's just
yeah, of
Patrick.
Course. No,
No, it's a very good strategy if you do. I don't know how you snuck in, but anyway, I'll ask the question. It's a good question. Maybe it's Patrick again. I don't know. But it says the value of the structural engineer is indexed to your ability to do more with less. Has Bollinger+Grohmann ever revisited old, in quotes, project through the lens of your new tools? And if so, what have you discovered? The follow-on is, I think of what Over Arif would do or learn now if he could revisit the early Pegasus computer sims at the Sydney Opera House.
Yeah, probably he could learn a lot.
That was Max apparently. I'm just hearing in the, he's logged in as Sascha. Because I sent the link. Classic. Max is undercover as Sascha.
Not Max. Great. No, I think in terms of revisiting old projects, I think we've done it once for an exhibition actually, where a lot of unbuilt projects were just revisited and reimagined in a different way, and how would it be possible to build them. I mean, some of them could be built just because they were too adventurous at the time, and so what would be, you know, a course of changing it so that we can build it now. But it would be definitely a great research work in itself, just to see how we could remodel some of the projects. How would this influence the overall architecture, and also increasing value or decreasing value of the project from the construction point of view. So I think that it's definitely great, but unfortunately most of the time people are just too busy to do this in the office. So and yeah, obviously coming from the very early days with the computational powers involved to compute the geometry and the structure for the Sydney Opera House, and now their computer filled the whole room. Most of the stuff we do is on my laptop, even sometimes on my phone. So there is definitely a speed up of computational powers itself, and it gives us then the freedom to explore just more iterations. The design space increases manifold, and this again comes in almost a problem in itself, because then we can pick and choose not only one solution as the solution. We have hundreds of solutions, and which one is then the best solution, no one really knows. And it's then coming down to certain aspects that the computer can't tell us, you know, so emotions maybe that you can create with the geometry and with the structure. How do you feel about it? It's one thing, for instance, that comes to mind. It helps you then to pick a solution over another solution. But at the end of the day, you have to overlay, and that's what you can do now in the near future, probably more than ever. Overlay all the different aspects of a project. You know, it's the structure, the thermal performance, comfort zones, the view, spatial arrangement. All of that becomes then one set that you can look at it almost instantly at once, and then make better decisions of, you know, your design.
Fantastic. I think we've covered all the questions in the chat. So unless Mohammed and Tim have something, I'll end in one last question, which is, sadly, engineers, like architects, are often burdened with having to wait for the problem to come in the door to us. If that wasn't the case, if you could be your own client or define your own project, what would it be?
My own project.
What's the thing you wish the next client would bring to you as a challenge to work on?
Yeah, I guess the next thing is definitely down the line that we work with a material that no one else has really touched on. There are really crazy materials out there right now. There are bricks made out of human urine, for instance, and things like that. You know, it's an incredible achievement to make a brick out of human waste that way. And just to get the hands on those materials and experiment with them would be awesome, and just to see what we can do with them. So it's not really about a complex geometry or a big elaborate building. It is really about the core understanding of those materials and how, you know, we could work with them. That would be great.
Fantastic, very revealing and intriguing answer. Thank you very much, Sascha. With that, I think we'll do a virtual round of applause. And we greatly appreciate your generosity, and we really look forward to when we can do this again and actually have you here in Sydney. So we can all go out and have a drink afterwards.
I would love to be in Sydney at one point again in my life, at least. And yeah, thanks for the invitation. It was really great to be there.
Thanks Sascha, and also just thanks for pushing the boundaries in Australia of what's possible and defining new things here.
Try my best.
You get the little team here, the support in the background.
Awesome. Thanks, guys. Okay.
Cheers, Sascha. See you.
Bye.